Hi, Hudson.
Oh,
Right.
hi.
Hello.
Hello.
See it again, I tell you. Okay, random numbers. Random.
What? The question. Random blood sugar.
Number generator.
6.
Maximum is 7. If your number shows up, you answer it.
Where is this?
5. So 1, 2, 3, 4, 5. Jacob.
9.
Oh,
What about the student's argument is correct?
The graph position.
What is correct about this student argument?
Just give me a
You had a minute. What does the student? Sorry?
I think it's incorrect.
No, they're asking you that there's some aspects of that statement that are correct, some aspects are incorrect. So which aspects of this student's statement are correct? I see you. Got my eye on you.
Well,
Let's look at the graphs. What does the student say? That more work is done in box B than...
it's correct in a way, but
Is more work done in box B?
the position of box B moves more than.
How do we find work done? This is a position time graph. What's the area under position time graph, Micah? C. So it's not work done.
that's area. It's speed.
The area under position time graph would be speed.
Others the
Wait.
slope is speed.
Wow.
Micah.
Because it's a unit. It's not a quantity.
Yes, thank you, Mr. Anderson. Anyways, the conclusion I was going to make from that is that the area doesn't help us in this situation, right? We know that work done is force times displacement, and displacement is going to be changing position. So, are they being pushed by the same force? Sorry?
That's not mentioned.
It's not mentioned. So, the position, how can we use the change in position to tell whether or not more work is being done? Mikhail, in which graph do we have more change in position?
The random number. Pick from you. Your special.
A.
We have more change in position in A,
Oh, no.
more displacement.
Maybe B.
Sure, in which graph do we have more displacement?
It's the same.
It's not the same.
No. Is the slope the same or not?
No,
It doesn't matter.
because the time is much less.
You use optical illusions like this.
Yes, Joe.
Isn't the displacement of box B greater because the distance between the two points is greater than
Between the two mark points. Okay. So good point, Jeho. Let's look at the distance, the change in position between these 2 points. Right? Versus the change in position between those 2 points. Why do we have a bigger change in position? Box B. So since that's a bigger change in position, what do we expect about the work done?
But we don't really know what the force. How can we make a conclusion?
We can assume the force is the same for both, because still work done is dependent on force times displacement. Yes, George.
Yeah, I was just gonna say that the higher the change in x, the greater the change in x, with the same force, is the greater the work done.
Yes.
So that's an aspect of the student's argument that's correct, that displacement relates to
Yes.
work.
You guys get that? Displacement is proportional to work done. So an increase in displacement will lead to an increase in work done. And since according to these graphs we see a bigger change in position, let me not say displacement, a bigger change in position in B than in A, then we expect more work done to be done in B. So that aspect of the student's argument is correct. Now, which aspect is wrong? Yes, Joe.
We can say that it's wrong because we're not sure if the same forces apply to both objects.
What does the student? The student doesn't say anything about force. The student says that he thinks more work is done in B because the displacement of B is greater than the displacement of A. That's what the
those
student
points,
says.
or like throughout the entire thing?
Between those 2 points.
Yeah, so if we,
So that's what the student says.
yeah, so since we don't know about like the force, we can't really make a conclusion.
If this was a graph, this would be a positive position, right? And this would be a negative position, correct? And here you would have a negative position and a negative position. What's the displacement in this case? Displacement is 1. What's the displacement in this case? So,
Those two are the same line.
sorry?
The negative 3 and the negative 2 are the same line. But it doesn't really make a difference.
So the displacement is
2.
2.
Negative 2.
So,
Or is it displacement can be positive or negative? Right?
yeah.
So it's negative or negative. Right? Oh no,
It depends,
yeah, it's positive,
it depends
yeah.
on what's your final position and what's your initial position. So if the final position is the top, then you'd have 2 minus negative 3, which is 5.
So you know the top is there.
And here, if the final position was the
Wait,
top,
how is the final position?
Yeah.
like I said, it depends on which one is your final position.
No, because of the time. In this case, it's negative.
Oh. So you're saying it doesn't depend. Minus positive 2, negative 5. And this one is, which is?
Wait, that is displacement?
Sorry? Displacement is final position minus initial position.
I thought displacement, I thought it was just change in x.
Change in position.
But I'll say that change in position there is positive, right?
Yeah.
Because it's going up.
Yeah.
Oh, goodness.
That's what I would think.
What's wrong with it? What's wrong with William?
You're just looking forward to a number.
So the final position is negative 1. The initial position is negative 3. So this is still 2. And that one is fine, right?
Yes.
So in which case do we have a greater displacement?
On the right.
Of box speed, yeah. So is there any part of
the
the students?
Of the great absolute value of displacement or just
Yeah.
of the great? So then it's box speed.
It's correct.
So what about the student's argument is incorrect? Nothing. Oh, are you going to say nothing?
Well, I mean, he's going into negative distance. And that means there's more negative distance. First distance, not negative.
We are thinking of the absolute value of the displacement. Like what's his change in position? What? Because the displacement of box B is greater than the displacement. Yeah, it is greater. By how many units is box B displaced?
5.
5. By how many units is box A displaced?
2.
2. Right?
But
So
it also
it's
goes
more
on for a
interesting
longer
to
time.
Yeah. Sorry?
It looks like box A goes like pushes for a longer time.
This one?
No, does it go longer?
It's
or
just
am I
between
missing?
the-
No,
It's
it's
between the
those
2
points.
points. It's only between the 2 black points.
I have a question.
We're wasting too much time on this.
This
Yeah.
is one of your trick questions. Because I think it's nothing, but I don't wanna. Because I've been too scared to say it this whole time. But it's one of your trick questions.
It's honestly an epic question.
Oh, no.
Why are they so they're like?
Why would they use crabs like that?
It's incorrect because
No. Nothing is incorrect.
They tricked us. Jim.
Everything he said is
They
correct.
thieved
So
us.
everything is right.
They tricked us.
But like, you can't know the net force without knowing the force.
Yeah.
We just assume that they have the same force.
Yeah, of course, of
The
course.
student said nothing about the force. The student only said something about work and displacement. He said the work is greater because the displacement is greater. And that's what we expect from this equation, that as when you increase displacement, you expect work to increase. So that's what the student said.
So they ask questions
There's
like that.
nothing
they
wrong
can
about
track
that.
it.
Yeah.
Oh my gosh.
so they just expect us to know what the person did.
They are testing your understanding of the concept. Every
How
time.
many How many response questions are there in the exam?
5? I want to say 5.
Okay.
Okay, let's get into this, guys. We're running out of time.
5 ABCD.
You read through this, right? So in the initial state of this, because they want us to compare where the thing is at this position and where the thing is at this position, in the initial state, remember, initial energy has to equal final energy, right? Initial mechanical energy,
What is that?
sorry?
It's page 105.
105.
Yeah, we skipped the whole movie.
This boy is a smart boy. Smart boy.
Black
Friday.
We can win a PS5.
Starts at 11, we can win a PS5 for 1,000.
1,000 shillings.
Started at 11.
1,000 shillings.
Exactly.
How long did you win the PS5?
It's a treasure hunt. It's a
The
treasure
entire
hunt.
junior shop. That is 1,000 shillings.
It's a treasure hunt.
Wait,
The
PS5
first person that
1,000.
finds it gets it. The
Yeah.
first person.
That's great.
You guys paid 1K.
Are you going to watch this?
Yes.
Man, you guys are lucky.
Alright, so the mechanical energy initial is equal to mechanical energy final, right? So ask yourself in the initial state, and I'm not reading through this because I asked you to read through, so I hope you read through and you know what's
Well,
going
you
on.
told us. Oh, wait.
Yeah.
You said two things at the same time.
Toy car is released from rest on a smooth track with a loop-de-loop. The car is released from a height such that it never loses contact with the track, so it never falls off the track. The system includes the car and the earth. Rotational effects from the wheels, friction, and air resistance are ignored. Yay! Draw and label a free body diagrams on the figure shown above that depicts the forces, not the components, exerted on the car as it goes down the ramp and at the top of the loop. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. Each force must be represented by a distinct arrow starting on and pointing away from the car. Fill in the energy bar chart below when the energy is first released from the height, when the car is released from the height h, and the final energy when the car is released from the top of the loop. Ooh. Okay. So, at this position, which forces are acting on the car? Up here.
Potential energy.
Gravity.
Forces.
Gravity.
Gravity. Any other force?
Friction.
Since it's on an incline, is there any other force? It's on an incline, so you have gravity. What other force do you have?
It said no components.
Yes, no components.
Wait, what?
If it was on a flat surface, you'd have gravity and normal force. Okay, so since it's on an incline, you have your force of gravity and where's normal pointing?
To the right side, up to the right.
Perpendicular to the surface, right? Which of those forces has a bigger arrow?
I don't understand. No, we don't.
Which of the forces has a bigger arrow?
Gravity.
Sorry? Yeah, gravity will have a bigger arrow. Because
Is that why we're writing?
Because they told you that the relative lengths of the arrows should reflect the magnitudes of the forces, right? it should indicate that gravity has a bigger arrow than the normal force. Okay?
And then we have to get FC, right? Or you didn't leave it.
Oh yeah. See, that's why I referenced you in the video. You see? So gravity and Fn. What about at this position?
FC.
FC.
Yeah.
FC is a component
Is it?
because
Yeah,
it's the
and-
net.
Oh,
It's the net of the forces that are acting on it.
I
Right?
have normal force like he said.
Yes. You have normal force. Where is it pointing?
Like downwards.
Downwards.
Gravity.
And then what else do you have?
Gravity.
Gravity pointing where?
No.
Which one is bigger?
Gravity.
Wait.
No.
Which one is bigger?
Gravity.
is same.
You're correct. Why?
I mean, the normal force in the ring.
Why is they equal? Why is that normal bigger?
Because since the normal force is also already smaller at the beginning,
Yes.
why would it just grow automatically?
That's true. There's no way the normal force is going to increase to be bigger than the gravitational force. The most that it will get is equal, and that's at this position, right? The most that it will get is equal. The other idea is when you're going around a loop, are you more likely to stick to the track or more likely to fall off the track? Fall off the track. So that means just intuitively that will give you less of a normal force. So you'll have a small arrow for normal force pointing downwards and another big arrow for gravity.
If so, if the normal force is bigger, you'd be more likely to stick.
If the normal force is bigger, you'll be flying through the track.
Wait, how? I'm confused, because the normal force would cancel it out.
Sorry?
How? Because the normal force would cancel out. Because yeah, I believe the gravity is bigger, but I'm saying just if normal force is bigger.
What would happen if the normal force is zero?
Oh yeah, normal
This
force is related to gravity. You can't.
That means you're not falling, but you're also not going.
That means you're in free fall,
Yes.
right? If the normal force is zero, the car is going to lose contact with the track, so it will fall, right?
Yeah.
So the converse or the inverse of that, if the normal force is too high, what's going to happen to the car?
The normal force is pushing away from it. I think it would fall as well.
I think it will push through the track.
Or see, the thing is,
Why
the way I think
would
of it is
strong
like,
it would stick to
the way I think of it is like, okay, let's say this, right? If I do, I can make this normal force greater than gravity if I add enough force into it. If I like a pressure,
Yes.
push it can make the normal force greater than gravity, and the tape doesn't work right. It doesn't mean that this is just gonna.
Depends on the system. Actually, it could.
It could, right?
Yeah, if
But
I get a
it doesn't
hammer
mean
and
it
smash
will.
the middle of the table, it will go through. On it.
But if you, let's say gravity is 9.8, and you push down with a force of 15, but the table will, right?
Yeah.
You're just stronger than the gravity. Your effect has more effect than the force of gravity. Or your force.
Think of something that will break the table, like a hammer, right? You smash the table with a hammer, it breaks through. What's happening to the normal force there?
I think he's right.
It's
Yeah, it's greater than gravity.
greater than gravity.
Yes, question?
Right?
So, what exactly is the force that keeps your car
On the track.
on the track?
Centripetal force
That is
is what's responsible for the car to go around the track. But centripetal force is the net or is a component of these two forces, right?
So what
It comes because of the effect of the normal and the gravitational force.
But it's pulling down.
Centripetal
And
force.
that's the tangential velocity. It's really high.
Okay, guys, I want us to move on. In this initial state, what energy does it have?
Full potential.
Full potential, right? And in this final stage, what energy does it have?
I would still say it has potential.
It does have potential, yes, but
It's more.
since this height is less than that height, does it have the full potential?
No, and some is.
What else does it have? Kinetic. Which one is bigger?
There is. I would say that's half the other hit.
I don't know if it's half. Does it say it's half?
Depends
I
on
don't
the
know.
height.
I'd say kinetics quickly, just because it's near the end of its.
Time?
Yeah.
But also because if we knew what this height is, we would be able to predict. As long as you draw this, right? And this, oops, it's very, very close to the other one. As long as you draw these two to show that the total of these two gives you that one, you're fine.
So even
Why do they're not the
Even if you drew them as equal, as long as your graph shows that this plus this is equal to the total of this,
does the width matter?
you'll get the points. Sorry?
The width doesn't matter. It's just the height.
Yeah. But I wouldn't, I'll draw them the same width. Same width and the heights to represent that this one, right, plus this one must equal that one.
Wait, my question is, if they're not at the end of the track, why are they equal to each other?
Why are they equal?
No, might actually get mechanical engineering instructional final.
Yeah. Yes, Jeho?
But when it came down, didn't it lose all of its potential energy?
At this point, yes, it lost all its potential energy. At this point right here, it had maximum kinetic, minimum potential. But since it's gaining height up to this point, then it gains potential energy, loses some kinetic energy.
Oh, so that's the bottom issue. Like,
Yeah, we're talking about this
A
position.
question.
Yeah,
So okay, let's say you and I are on the ground right now. Do we still have potential energy? Or no?
depends on the reference. If the reference is at sea level, if the
So if
reference,
say it's low, that's all.
yeah, it depends on the reference. Yeah.
Why was the kinetic larger than the potential?
Why is the kinetic larger than the potential?
It looks like it's half of the height. So
It does look like that. So, no, I said as long as you draw them to show that they add up to give you the other thing, right?
Yeah.
So if you wanted, you could have drawn half-half. That's still fine.
Yeah,
Because we don't have enough information to for sure tell which one is bigger at this position, right? So as long as you draw them to show that they add up to the other one. Explain why the release height must be greater than the diameter of the hoop. Explain, citing the bar chart, right? Why should this height be greater than the diameter of the hoop? You just showed it.
Because the diameter is the same as the height. So if the height is greater than the initial height,
Yes.
there wouldn't be enough kinetic to reach the point.
Yes. There won't be enough energy transfer.
Wouldn't make sense.
Sorry?
That mechanical energy equation wouldn't make sense if
Yeah.
that was reached.
If this initial release height was just here, then this car would only have enough energy to get it up to there, right?
Yeah.
Because the potential energy it loses here is the potential energy it will gain here. So this release height has to be higher than the height of the loop for the car to make it around, because it has to gain, potential energy to get to that height. So you can put that in words. What time is class end? 10.
Yeah.
We can do this.
At 11:35,
We can do this. Okay, you guys, you write later. Let me first explain.
I'll forget.
Carlos determines that the normal force the car experiences at the top of the loop can be determined by that equation, right? Fn equals 2mg out of h. To test the equation, he releases the kart from various heights and records the normal force at the top of the loop from the sensor in the track. The graph is the student's plot of the data for Fn, a function of height. Is this data consistent with the equation? Please look.
Which one is that in equation?
I will post this video, so please let's pay attention.
No, but is this a push? Is this?
It's not.
Okay.
It's Carlos's equation. Carlos tries to determine that this is the equation for normal force, right? 2mg divided by height. Now, Carlos tests this equation by doing an experiment, and this is the graph he gets. According to this graph, what is the relationship between normal force and height? Would you say it's directly proportional or inversely proportional, according to this graph?
Inversely.
According to the graph.
height.
What? Oh.
As the normal force increases, the
Yes.
height increases.
Yeah.
So is it a linear relationship?
Yeah.
Yes. So according to his graph, this is the relationship you expect.
Yes.
But according to his equation, what's the relationship that he has?
It's inversely.
It's inversely proportional to the height, right? So is his equation consistent with the graph?
Nine.
No, right? So that's the idea you're going to use, that his equation shows an inverse relationship between normal force and height, but his graph shows a direct relationship between force and height, so therefore the data is not consistent with his equation. Moving on, Blake suggests that regardless of whether or not the above data are consistent with the equation could be incorrect for other reasons. Does the equation make physical sense? So let's see. So Blake wants to give Carlos some props. Does the equation make physical sense? He says it's 2mg divided by h, right? Now, the hint here, or the clue here, okay, is this word physical sense, right? If it makes physical sense, one of the things that should be true is that it should be dimensionally consistent. What that means is the dimensions of this should be the same as the dimensions or the units of that. Correct? Because if I write an equation like, when I say dimensions, I just mean units. Sorry, I confused you. So if I write an equation like F equals MA, I know the units of force are newtons, and what I expect this side should also give me newtons. So check if this equation is, if the units are consistent. I know normal force is a force, so the units are what? Newtons. So let's check this side if the units are also newtons. Mass is kilograms, G is meters per second squared divided by meters, right? So this is kilogram, oops.
That's just kilograms per second squared.
Kilogram what?
Per second squared.
Per second squared. Is that the unit for newtons?
Yeah.
No, kilogram meters.
Is that the unit for newtons?
No.
So first of all, the units of this equation are not consistent. So the equation doesn't make physical sense, right? This is not a newton, yet he's saying that it's equal to the force. So that equation does not make physical sense.
This makes sense. But force is what you meant?
Newtons.
So every time they're talking about physical sense, we're gonna have to check.
Force is newtons, and a newton is kilogram meters per second squared. The force that it takes to move a kilogram through 1 meter in 1 second. Yeah. Yes, you can. Physical sense, that's one way you can think about it. Another thing you can say here is that his graph does not reflect his equation. Or, physical sense. Normal force, do you expect normal force to increase or decrease with height?
Decrease. If height increases, I'll expect normal force to decrease.
So that again.
Because of normal force, it has something to do with gravity, yeah? And as height increases, gravity increases. So I'll expect the normal force to decrease as well.
Yes.
Feels so wrong.
Man, no.
Yeah, the face. Oh my gosh, I'll never be able to get this down.
No.
You saw his face. You saw yourself.
I saw it.
You saw your eyes.
Georgie, you took me in circles just to say direct relationship. So I was
trying to
following
explain
your circles all around, like I was like 2 steps behind each time you were talking, trying to check the consistency.
So,
And
all
then
I
at the
saw
end of
was-
the day, you say directly proportional. I was like, okay.
Not directly proportional.
So you
I'll
say
say
inversely proportional.
when height increases,
Mhm.
normal force decreases.
But that will be consistent with this guy's thing.
No, but not consider the graph and the other thing aren't
Yeah,
consistent.
yeah.
Those two are not. But I just said that I'm saying that you could have added another variable. You could have written another variable.
Actually, you're trying to answer this part. The equation could be incorrect for other reasons. Oh?
Yeah, you could have written a variable.
Yeah. Okay, is this the last one?
Yes.
What would happen if Carlos released the car from a height of 0.8?
What colors do
Did it say
Yes.
the height?
I don't think it would, because if you look at the graph,
Yes.
it doesn't line up with the linear. He had to start at like 30. He had to start at 1.5 meters.
Are you guys seeing that graph?
Well, Micah's the green.
Yeah, okay, smart. You guys all seeing that graph?
Yeah.
If I try to draw a line of best fit through these points, that's not the one. If I try to draw a line of best fit through these points, where does it touch the x-axis?
At like one.
Whoa, how did you draw that?
What?
Like
He is the
Let's
graphic.
use the
line
next
twelve.
one.
You know what's the
I'm not good, Georgie. So if that line cuts at, so it shows you that when the height is 0, no wait, when the height is 1, the normal force you get is,
0.
sorry, Micah, can you repeat your answer?
Because point 8 isn't where he started.
Yeah.
It's not the initial value.
Yeah. And he actually, his first measurement for normal force didn't come until he had, what's this? 1.5?
0.8.
Yeah, so 0.8 is here. 0.8 means the normal force is 0. 0.8, according to this graph, corresponds to a normal force of 0. Correct?
Why is that?
Because this is a graph of normal force versus height, right? Height is 0.8, normal force is 0.
Of negative, right? A height of 0.8 is negative.
No, it's right here. Height. This is the height axis.
Well, no, but think about it like this. You can just say that, I don't know, this 1.2 is there for 60, right? It has to follow the line, right? And 0.8 would be negative.
Oh, yeah. Thank you.
But why would normal force be negative?
Because of the line of backwards.
Wait, but what is it trying to prove? That's my question.
What this is trying to prove to us is that at 0.8 there is no way he's clearing the track, because even at a height of 1, right, and this is what I should have been saying, even at a height of 1 he has a normal force of 0, and that's enough for you to conclude, because you know if you have a normal force of 0 you are in free fall,
Oh, I see.
weightlessness, right? Normal force of 0, you're weightless, in free fall. If you're in free fall, do you have contact with the track?
No.
No. So, because even at 1, where the line touches the axis, even at 1, you have a normal force of 0. So therefore, at 0.8 for sure, the cut. So at 1 is where it loses contact with the track. And if that's happening at 1, then at 0.8 for sure, you are not on the track. You cannot make it around the loop.
And this thing is taken at the top of the loop, right?
Yes.
Oh, I thought it was taking up at the start, so that wasn't making sense to me. But I get it now.
Wait, is it at the top of the loop?
No, it is at the top of the loop. It says.
Yeah, from a height of 0.8. So no, he doesn't make it. We have justified it using relevant features from the graph. Guys, we made it. I will post this video